Hello, my name is James Ryland, and this is going to be the first lesson, part 1 of my series on learning how to be a neural network practitioner. One of the most important things to understand about neural networks when starting out is the neural metaphor. One of the most important parts of getting into neural networks is understanding that we are actually imitating real biological neurons and systems of neurons with our models, even though we use quite a lot of abstraction. So even if you don't want to use real biological or realistic neural models, we are always using the metaphor of neurons in order to build our models. So let's take a look at a real neuron. This is a real neuron. It has a lot of different anatomical parts. Okay, we're going to look at the parts we're interested in one by one. So in the green, down at the bottom, you have what are called axon terminals. These carry information from other neurons to this neuron in order to send their activation levels to this neuron. So axon terminals in green. In red, we have dendrites. These are where axon terminals connect to, and these are part of the cell we're interested in, the neuron we're interested in. They carry information from the axon terminals to the neuron proper, but they modify the signal. They are what are going to change when an organism learns something. And the dendrites finally carry the information to the cell body. The cell body is going to sum up those weighted signals and send out its own signal to other neurons, depending on how large or small the value was. Or it might be some complex transformation of that summation. So to get a little bit more abstract, we'll often call the inputs to a neuron S, and we'll give a subscript to each individual input. So S1, S2, S3. And then we'll call the dendrites, which weight the inputs, W. And we'll give each one a corresponding index to pair it with each corresponding input. So W1 and S1 are a pair, W2 and S2 are a pair, etc. And then the output of our cell we're going to call, for this case, R. In my course, I'm going to typically use R to denote a linear neuron. So what do I mean by linear? A linear neuron is just a linear function of the inputs. We're going to put that equation up in just a bit after we talk about our more schematic neuron. So now that we have all these parts, let's transpose them onto our abstract representation of a neuron that we will typically see in the rest of the course. So here's an abstract model. We have a series of circles and edges. Each circle represents a neuron, which has a response value. And each edge represents a connection from a neuron to another neuron. The neurons at the bottom are going to be our inputs, just like the axon terminals were previously. So those we will call S again. And then the lines, or the edges, are our connections, our weights. So we'll call them W again. And the neuron at the top is going to be R. So now we have all the basic parts of the neuron that we're interested in modeling in order to have our neural unit for our neural simulations. So remember when I called this particular neuron linear, what I mean by that is the function we're going to use in order to get its output or its response is going to look like this. So all we're going to do is add up W1 times S1 plus W2 times S2 plus W3 times S3, and that will be our response. And here we just denote the same thing with the summation sign over the index I. This is a linear function, and we'll talk more about linear functions later on in the course because it will be helpful to have a very precise mathematical notion of what's a nonlinear function and what's a linear function. But for right now, generally speaking, linear functions will be restricted to linear summations that look like this. But that's not always going to be the case. Very shortly, we're going to look at neurons that are nonlinear. So that means we're going to take the weighted summation that we have here, and we're going to replace it, well, we're going to make it the input to another function. And typically in this course, when talking about very simple 1 or 2 neuron examples, I will call nonlinear neurons Q. So we'll change R to Q. So Q is equal to some function f, which we haven't defined yet, that takes the weighted summation that we got previously as an input. So we will definitely want to get to nonlinear neurons very shortly, because they're actually where the field of neural networks gets quite interesting. But for now, we're going to stick to linear examples. Don't worry, we'll get there soon. Some takeaways to remember are that we use schematic versions of real biological neurons. We abstract away a bunch of their actual biological details in favor of simple mathematical constructs that are going to make our lives a lot easier, and going to make it a lot easier for us to analyze the behavior of these systems and design them in the first place. But these simple little schematic neurons are the units for some of the most sophisticated machine learning algorithms ever made. And you'll find out that their power is quite incredible. Okay, well, I think that's it for this tutorial. The next tutorial will introduce several kinds of notation for talking about linear summations.